So today is my next lecture. We spent a couple of lectures developing the homological algebra constructions with the promise to use them later in our study of deformation quantization. Actually, the most, I think, example where this homological algebra plays the most important role is Kontsevich construction, of course, and not just it, but rather, I'd say, the way Tamarkin proved this Kontsevich construction. But it's pretty far remote from the place where we are now. It would take us a few more lectures just to develop the theory we will need to prove this theorem. So I begin, I prefer to give a very concrete and very naive example where homological algebra plays the role in deformation quantization. It might be pretty simple. You might think it is redundant, but in fact it is, I think it's kind of, let me say it, iconic example of example of homological algebra in deformation theory. Iconic and I'd say epitome of homological algebra methods in deformation theory. So I begin with something very simple. So, okay. Let A be an associative algebra. I'm beginning with something pretty abstract. As I already defined, the deformation of A, to cut the long story short, in fact, one can speak about arting rings, about some representable functors and so on, but just to be as explicit as possible, let's call deformation of A any algebra, say script A, which is linearly isomorphic to a space of formal power series in variable h bar with coefficients in A, and which is equipped with an associative product. H bar linear product. Such that for any A and B in A capital, the product A star B begins with the usual product A times B in A plus some sum, well, certain sum of a variable k from 1 to infinity, h bar times 2 to the power k, bk of ab. That's not the most abstract, the most general definition of deformation of an algebra. I say, let me say that, in fact, in modern literature, you'd find some discussion of arting algebras, arting, representable functors, and so on and so forth. And of course, this is probably more correct way to speak about deformations. But to cut the long story short, let's just restrict our attention to this case. Then we have the following series of homological abstractions. Namely, consider the associativity equation. A star B star C equal to A star B star C. And let us expand this equation in respect to the powers of the variable h bar. So the first term is h bar to the power 0. It will correspond just to equation A times B times C equal to A times B times C, which of course holds for all A, B, and C, since A, capital A, is an associative algebra, right? So now we turn to this next power, the first power of H. And this is not trivial already, but pretty simple. So we begin with the internal part. How can we get the first degree of H here? We just take B1 of AB. So in order to restore, to preserve the degree 1 of H bar, we can only multiply this term by C, nothing else. However, there is yet another way to obtain H bar here. That is, to this end, we take A times B inside the parenthesis, but then we apply B1 to the pair A times B and C. So these two terms account for all the terms with H bar with linear in H bar on the left. So the terms linear in H bar on the right will look pretty much the same. Namely, we have A times B1 B comma C plus B1 of A comma BC. And now I think everybody will see the equation delta of B1 applied to A, B, C equal to 0. So this equation is equivalent to just the equation delta of B1, A, B, C equal to 0. Is equal to 0. Here I regard B1 as an element in C1 of A, sorry, C1, C2, A comma A. And this equation just means that B1, so equation 1 means that B1 is a cocycle. You see, it means that there are as many ways to extend the associative product from A to script A, as many in degree 1, as many different cocycles there are. Nice. So let us go on. Let's turn to the second term. So H bar to the power 2. So the quadratic terms with respect to H bar. How can we get them? It is a little bit more complicated. So let me begin with quadratic terms inside the parentheses. You can get the quadratic term if you consider B2 of A comma B. And then you just multiply it by C. Or else you can take B2 and apply it to A, B, comma, C. That's also possible. And that accounts for the terms similar to these two terms, right? But unlike the previous step, here we still have another opportunity to obtain a quadratic term. And that is just to take B1 of A, comma, B, comma, C. And that's the left-hand side. And on the right, we'll have pretty much the same formula, except for the fact that A, B, C will be a little bit permuted. So first term will look like A times B2 of B, comma, C, plus B2 of A, comma, B, C, plus B1 of A, B1 of B, comma, C. Let us collect all the terms with B2 on the right, or on the left, doesn't matter, and all the remaining terms on the right. So on the left we'll have, as one readily sees, just delta of B2 of A, B, C. Meanwhile, on the right, we'll have B1 of B1 of A, B, comma, C, minus B1 of A, B1 of B, comma, C. So the left-hand side is clearly understood. Meanwhile, let us speak about the right-hand side of this formula. So let's turn to the right-hand side of this formula. I hope you can recognize something pretty familiar here. If you remember, there were operations circle with subscript I, which we described last time. Let me recall that there are two operations, circle subscript I in this case, circle subscript I, subscript 1 of B1, sorry, B1, comma, B1, B1, right? Which is an element in C3. And on the elements A, B, and C, it takes the values B1 of A, comma, B, comma, C. And similarly, there is B1 circle subscript 2, so sub 2, B1, which again is an element in third, is a degree 3 cochain. And on the elements A, B, and C, it takes values B1 of A, comma, B2, B1 of B, comma, C. So, as you see, the right-hand side in this formula looks like on this formula, let me put star. Looks like B1 circle 1, B1 minus B1 circle 2, B1 applied to A, comma, B, comma, C. Let me recall that the operation like this also appeared at the previous lecture, and it was called just circle without the subscript. Namely, if we take a P cochain phi and a Q cochain psi, then phi circle psi look like sum for I from 1 to P phi, sorry, minus 1 to the power P I think I minus 1, right? I thought, no, p minus 1. Yeah, like this. I minus 1, I think. Yeah. Phi p circle I psi q. Let me. So I think if you have my lecture notes, you can check the signs again. The signs are always a big problem here, but here they are put correctly, because if you just look here, you'll see. No. Sorry, that's not p minus, just p. Yeah, p. Here they are put correctly. P. No. I think it should be p minus 1. And the reason for this is pretty clear. Because in our case, p is equal to 2. So p minus 1 is equal to 1. Right? In other words, B1 circle B1 will look like B1 circle 1 B1 minus B1 circle 2 B1. Right? And therefore, this sign should look like this, I think. For instance, here, I is equal to 1, so minus 1 to the power p minus 1 times I minus 1 is equal to 1. And here, I is equal to 2, so minus 1 to the power p minus 1, I minus 1 will be equal to minus 1. That is correct. In case there is a misprint, please let me know. I'll check this. Okay? So, this right-hand side can be now abbreviated further just to B1 circle B1 of A, B, C. Finally, there is one more thing. It's actually not sufficient for us yet. It's not the best way to write this equation, just because the operation circle is not, does not have that good properties, algebraic properties. It's not as good as the Gerstenhaber bracket we described last time. So let us consider finally the Gerstenhaber bracket of B1 and B1. So let me recall that the Gerstenhaber bracket of phi p and psi q is equal to phi p circle psi q minus 1 to the power p minus 1 q minus 1 psi q circle phi p. So in our case, the Gerstenhaber bracket of B1, B1 will look like B1 circle B1 minus 1 to the power 1 B1 circle B1. And it's our good luck, or maybe not good luck, but rather the hidden symmetry of all being, right? That minus 1 to the power 1 is equal to minus 1. So what we have is sign plus. The sign is plus. So the right-hand side means, so it means that the right-hand side of this equation takes its final form. It is equal to 1/2 of B1, B1. Nice. And we come up with the following statement. There exists an extension of the formula A star 1 B equal to AB plus H bar B1 AB, where B1 is a 2 cocycle, 2 to an associative 2. Okay, let me put it like this, to the formula, or probably to a formula, I don't know. It's a little bit confusing. The formula A star 2 B equal to AB plus H bar B1 of AB plus H squared B2 of AB, such that the associativity equation holds up to degree 2, if and only if the class of the Gerstenhaber bracket of B1 with itself in the degree 3 cohomology of A with coefficients in itself, Hochschild cohomology, of course, is trivial. Well, of course, what does it mean that the class of this expression is trivial? Well, first of all, since B1 is a cocycle, this is also a cocycle, right? Because the Gerstenhaber bracket verifies Leibniz rule with respect to the usual, with the usual boundary map differential. So it determines a class in degree 3 cohomology. So the equation written here means that the class, that the element is in fact not just closed, that it is exact. So the class of this expression in cohomology should be trivial. And vice versa, if the class is trivial, then there exists an element in degree 2 such that its differential is equal to this cocycle. And we can use this element B2 as the second term in our formula. Now we can go on. For instance, in degree 3, H bar when you take H bar to the power 3 cubic terms in H bar, we have the following equation. Delta B3 of A, B, C should be equal to 1/2 of the Gerstenhaber bracket of B1 and B2. Well, just to see this, let me just briefly explain this. So the equation will look like A times B3, B3 of A, B, C plus B3 of A, B, C plus B1 of A comma B. Yeah, sorry, I quite forgot. So yeah, B3. Yeah, it should be like this. B2 of B1 of A comma B comma C plus B1 of B2 of A comma B comma C, right, is equal to B3 of A comma BC plus B3, A comma B3 of B comma C plus B2 of A comma B1 of BC plus B1 of A B2 of BC. So now you do the same trick. You put all the terms with B3 on the left, all the remaining terms on the right, and you reinterpret the terms on the right as this kind of thing. It's actually not important whether you put B1 or B2 on the right, because you remember, and it is equal to minus 1 to the power 1 times 1 B2 B1. So it's not important whether you put B1 or B2 on the left, right? Okay, nice.
It's look like Fourier-Cartan equation.
Precisely. Fourier-Cartan equation. That's how it's called. It does not just look like Fourier-Cartan, it is called Fourier-Cartan. Okay. So what do? I have this equation, and again, on the right, we can, it is easy to see that the right-hand side of this equation actually verifies the condition that delta of the right-hand side vanishes. Delta of B1 comma B2 is equal to 0, and that is because of the Leibniz rule. You see, have delta of B1 comma B2 should be equal to delta of B1 comma B2, and here we have plus or minus. I actually don't care whether it will be plus or minus B1 comma delta B2, right? The first term vanishes because delta of B1 is equal to 0. B1 is cocycle, as you remember. Now, what we have is plus or minus 1/2 of B1 comma B1 comma B1. And this is so because delta of B2, let me recall that delta of B2 is equal to 1/2 B1 comma B1, right? So we have this term, but this term is actually 1/3 of the graded Jacobi identity. And so on. I don't want to write this. And this is equal to 0 because of the Jacobi identity. So we have this equation here, and we conclude that the right-hand side of the equation number 2 is again a cocycle. And again, the condition that we have here looks like a cohomological condition that there exists B3 making the expression A star 3b equal to AB plus H bar B1 of AB plus H squared B2 of AB plus H cubed B3 of AB into an associative after degree 3 star product if and only if the cohomology class of this element in degree 3 Hochschild cohomology of A with coefficients in itself vanishes. We can go on indefinitely in this direction. If you want, you can check it yourself, that in general, you'll get an equation of the form delta Bn plus 1 is equal to 1/2 sum, damn it, P less or equal to Q, and P plus Q is equal to I don't even think it is necessary. Sorry. I think it is not necessary to put 1/2 here in this way, but if we want to preserve 1/2, it will look like this. To n plus 1. Yeah. BP, BQ. Right. What's the problem? No. Hence, the right-hand side is closed with respect to delta. Hence, there exists Bn plus 1, which we need if and only if the class of the right-hand side in H3 of A comma A is equal to 0. This is not very useful, unfortunately, because, well, of course, if the third cohomology of the algebra A is trivial, which is pretty rare situation, but still can happen, then these equations always have solutions, and we always have a deformation. But in general, these right-hand sides, the proof that the right-hand side of these formulas can be made trivial is not very easy. I'll do this in a very particular case a little bit later. Now let us speak about the uniqueness of the star product. As I explained, two star products, star 1, well, star and star prime, are called equivalent if and only if there exist a formal power series of maps, linear maps, T of A equal to A plus H bar T1 of A plus H2, H squared T2 of A, and so on, such that T of A star B is equal to T of A star prime T of B. Right? The inverse of T is obtained by inverting this formal power series. and that's not very hard. And it is possible because the first term is just identity operator. Now, Ti are maps from A to A, linear maps. So again, let us look at this equation. Now let me put it like number 3, and let's consider its terms one by one, taking all degrees of h bar on the left and on the right. So what do we have on the left? In degree 0. Well, that's pretty simple. It's just a b is equal to a b, so nothing interesting. What about h1? That's more interesting. How can we get h1, the linear term? Well, first of all, we can apply t1 to a times b. So a1, t1 of a times b brings us a linear part in h bar. But also, we can get it from applying t0, that's identity operator, to b1 of a and b. So that's what we have on the left. And on the right, we'll have t1 of a times b plus plus a t1 of b. But also, we can get h bar from applying b1 or b1 prime to a and b. And then, and without any t here inside, right?
We obtained it from multiplying to series, right?
Yeah, if you want. So, what do? We put b1 and b1 prime on one side. It will give us b1 minus b1 prime of ab. And on the right, we'll have a t1 b plus minus a1 t1 ab plus t1 a b. So the right-hand side looks like delta of something. And we conclude that t exists up to degree 1 if and only if the difference of b1 and b2 is cohomologous to 0. b1 and b1 prime. Sorry. Exists t1 if and only if the difference b1 minus b1 prime is again equal to 0 in h2 of a comma a. So there are as many different first terms, well, essentially different, which cannot be sent into each other by some transformation, by some equivalence relation. As many different cohomology classes in H2 there are. Well, let's go one step further. Consider H2. So what do we get? We get T2 of AB, right? But we can also get degree 2 from implying T1 to B1 of AB, and also by applying T0, which is just identity, to B2 of AB. And that's on the left, but what they have on the right, we can get the same degree 2 from T2 of A times B plus A times T2 of B. But also, we can get it from applying B1 to T1A B plus B1 A T1B. And finally, you can just apply B2 to A and B. Right? Of course, on the right, we have primes. I forgot about this. That's important, but we need to remember, but I forgot, sorry. So again, if we collect all the terms containing T2 on one side, we'll just get delta T2 of A, B. Meanwhile, all the other terms, if we collect them on the right side, will look a bit more intriguing. It'll be B2 yeah, I think as far as this, the only problem is I think the sign is incorrect. It doesn't change the formula, but the sign is incorrect. The conclusion is the same, of course, because if B minus B prime is trivial, then the same is true about B prime minus B. But sorry, but just to be on the safe side, let's correct this. Let's take care of the sign. So what do I have on the right then? It's B2 prime. Sorry. So yeah, it's B2 minus B2 prime. So how do we get it? So again, it's a bit difficult to do this. Oh no, the sign was correct. And the same is here, yeah? Yeah, I put B2 on the left, right. Yeah, I am confusing the signs because I put T2 on the left here, while I was trying to put T on the right. So let us do it like this. So it's B2 minus B2 prime. That's correct. Of AB, right? And also, what we have is B plus T1 of B1 AB minus B1 prime of T1 of A comma B minus B1 prime of A comma T1B. Yeah, that's correct. Finally. Nice. Yeah. Now, on the right, we again have a pretty long formula, but it is easy to check that the differential, the Cauchy differential applied to this expression vanishes. So where is the chalk? Where did I put the chalk? I don't see it. Okay. For instance, delta of B2 minus B2 prime is equal to 1/2 of B1 comma B1, right? Minus 1/2 B1 prime comma B1 prime. Okay? Here it is. As far as the second term is concerned, second part is concerned, sorry. Before I proceed, I quite forgot to do one thing. Yeah, I'm sorry for this. It makes, because of course I can do this in this form as well, but that makes the whole thing look much more complicated. So let us assume I have chosen T1. Choose T1. When we have chosen T1, we can consider the product star double prime given by the formula star double prime AB is equal to 1 plus T1 minus first applied to T1 of A star prime T1 of B and if you expand, what you see will be like this. Sorry, of course I forgot about H bar. Not T1, 1 plus T1, H bar T1. And here also 1 plus H bar T1 of B. Okay? So here's what we do. So if you expand it, you'll see that A star double prime of B will begin with A, B plus B1 of AB plus B2, sorry, H bar 1 plus H2 H bar squared B2 of AB double prime plus something else. But what is really important, it is that B1 here and in the formula for the usual star product, the original star product, will coincide. You remember that the original formula was, the original equation was that T applied to A star B is equal to T of A star prime T of B. So I just took the first term in this equation. I changed the right-hand side with the first term. So what I obtain will match with the left-hand side up to degree degree 1, up to the linear term in H bar, right? So it means that we can assume by passing from from star prime to star double prime that B1 and B1 prime are the same. Okay, sorry. So when we return to this formula, I can erase the prime on the right-hand side, here and here. Sorry, here and here, but here I'll preserve it. Okay? Nice. So finally, I can erase prime here and here, and now it looks very familiar. As you see, what we have here is again just the Gerstenhaber bracket of T1 and B1. So the equation is delta T2 is equal to B2 minus B2 prime plus the Gerstenhaber bracket of T1 and B1. So that's much more convenient for us. What do we get? We get, now again, when we apply delta to the right-hand side, we see that delta of B2 minus B2 prime will be equal to 1/2 of B1 comma B1 minus B1 comma B1. That's trivial, right? As explained. Plus delta T1 B1 plus or minus T1 delta B1. But delta B1 is trivial, as you know, because B1 is a cocycle. This term vanishes, and delta of T1 is equal to, we can also, is equal to 0. We can actually take T1 equal to 0.
Why?
Because in degree 1, we're already done. So as you see, there exists T2 if and only if the class of this difference B2 and minus B2 prime. But this B2 prime is not the original B2 prime. It's the B2 prime we obtain from this combination. Right? So there exists T2 if and only if the class of this difference is trivial in cohomology. Okay, nice. And so on. At the next step, we take, first of all, we modify our star product further. Star double prime to star triple prime by taking, well, A star triple prime B equal to 1 plus h bar squared T2 minus first applied to 1 plus h bar squared T2 of A star double prime 1 plus h bar squared T2 B. Right? Then again, A triple star triple prime B will be equal to AB plus B1 A h bar B1 AB plus h bar squared B2 of AB plus something H3 H cube B3 triple prime or something AB. But you see, again, the difference will appear only in degree 3 and further. Right? So we take mu t, the third implication of t, as identity plus h bar to the power 3 t3 for some t3, and repeat the same operation. We see that B3 minus B3 triple prime is closed in in C2 of A comma A. And there exists T3 we need if and only if the class of this difference in H2 of A comma A is trivial. Okay, nice. We can go on and on. So at the nth step, we first modify the star product so that the new star product would match the given star product up to degree n. It will match with the original star product up to degree n. So at the n plus first step, first modify star product so that star n matches with the given star product up to h bar to the power n, including h bar to the power n. Then consider the equation. Consider t equal to 1 plus h bar to the power n plus 1 t n plus 1. And take the terms in degree n plus 1, and that will give us the formula delta of t n plus 1 is equal to b n plus 1 minus b prime n plus 1. And that is exactly what we need, right? And so on and so forth. In other words, we see that there exist as many different ways to extend from degree n to degree n plus 1, assuming that the extension exists. As many essentially different ways to extend our star product from degree n to degree n plus 1, as many different classes in the cohomology of degree 2 there are. Nice. So again, the main problem of this approach is that in most situations, a cohomology in degree 3 is pretty large. But sometimes it is possible to circumvent this difficulty by considering some additional properties, some additional structures of our algebra. And here is the basic example where this actually works. So let M be equal, before I proceed with the example, let us consider the particular case where the algebra A is just the algebra of smooth functions on a Poisson manifold, on some manifold. So let A be equal to the algebra of smooth functions on some manifold, right? Then B1 is closed, right? Hence, by the Hochschild-Kosten-Rosenberg theorem. So first, B1 is closed by Hochschild-Kosten-Rosenberg theorem in the form I described last time. I forgot to say. And of course, then all Bn will be not just elements of C2 of AA, but they will be from the differentiable part of this Hochschild complex, as I explained last time. They should be differentiable. So in this case, when B1 is closed, we can apply the Hochschild-Kosten-Rosenberg theorem in the form I described last time. And hence, B1 will be equal to the symmetrization of B1 plus delta of certain element in degree 1. Right? Anti-symmetrization. So the cohomology class of B1 will be equal to the cohomology class of its symmetrization. Right? And it will be an element in, by Hochschild-Kosten-Rosenberg theorem, in the space of bivector fields on M. So it's a bivector field, as we know. Then, when you go from degree 1 to degree 2, as you remember, the condition was that the class of B1 commuted with B1 in H3 of A, comma A should vanish. But in our terms, so let us denote this by pi. In our terms, since we have identified this class with the bivector field, we should also identify the image of the Gerstenhaber bracket on cohomology, in cohomology, with Schouten bracket in cohomology. So we conclude that the Schouten bracket of bivector pi with itself should vanish in T3 polyvector fields on M. In other words, whenever we try to deform the algebra of differentiable functions on a smooth manifold, the result, the deformation will exist. The first term, I'd say, the first term will always be given by a certain Poisson structure. Moreover, sorry?
The deformation means that we introduce the formal
Yeah, the formal parameter. All throughout the course, I'm only speaking about formal deformations. I do not speak about some analysis. I do not speak about actual Hilbert spaces and operators on Hilbert spaces. This is algebraic construction, but it's pretty interesting because it actually depends on geometry of the manifold. It's not just pure algebra, I'd say. It's some geometric construction.
because we consider the cohomology.
Sorry?
Because cohomology have taken into account. Or
Sorry?
Where does the geometry arise?
Because we're speaking about manifold.
Ah, so okay.
What do you call geometry?
No, I thought that maybe some cohomology classes or something
I mean,
might depend on it.
of course, I mean, the Poisson structures are bivector fields. So bivector fields are geometric objects. The condition that bivector fields are Poisson is pretty non-trivial geometric abstractions, pretty non-trivial geometric structure, pretty non-trivial geometric condition, right? Moreover, if you look at the, if you try to consider further the other abstractions that exist, that appear there, for instance, you can do this in symplectic case. In that case, you can actually describe the abstractions in a very geometric way. And in that case, the abstractions that appear will have very interesting geometric nature. They will be given by so-called V class of the symplectic manifold, which is pretty interesting, I'd say. Okay, let's go on. So in the case of the algebra of smooth functions and manifolds, we see that all deformations are initiated by some Poisson structure. Right? Moreover, if B1 and B1 prime are cohomologous, then the Poisson structure will be the same So in particular, but on the other hand, if we take, if we consider this difference, so this will be B1 and this will be B1 prime, right? And of course, B1 and B1 prime are cohomologous. But when they are cohomologous, the corresponding star product will be equivalent, right? So we can always assume so the corresponding star products will match in degree. So by passing to equivalent star products, we can always assume that the corresponding star products match in degree 1. For instance, in this particular case, if we take B1 and B1 prime as I describe here, we see that we can always replace our star product with something. We can think that the star product begins with the form, with the expressions which are already written several times at the blackboard. So the first term is just the usual product of functions, but the first term will look like h bar divided by 2. So this 1/2 appears from the fact that I symmetrize it here. And symmetrization and anti-symmetrization, it actually includes division by 2. H bar divided by 2, A, comma, B. The Moyer product was introduced from totally different. It was the motivation for this, right? I could have given this motivation from the very beginning. So consider the general procedure of deforming an algebra, and then apply it to the particular case of the algebra of functions on a manifold. Then we'll have this. So the original form of deformation quantization is actually restored from this general principle, right? So let me now finally give the example I promised. So let M be equal to G check, and I take A equal to the polynomial functions on M, that is the symmetric algebra of G. In this case, all the constructions we discussed are applicable, can be applied. However, in this case, there is one important feature of the Hochschild cohomology which makes it possible to compute the abstractions, calculate the abstractions eventually. Namely, the algebra A is graded. I will also consider not just the generic complex of the algebra A, even though A is algebraic, even though it's the algebra of polynomials, but I still consider only differentiable cochains on A. It is a good thing that they actually, well, the notion of differentiable cochain on A and differentiable cochain on any smooth functions on G check match and coincide. So consider this. And I will say that an element phi in C dot diff A comma A has degree k. Well, where k is some integer number. If for all homogeneous elements We're running out of the chalk again. Chalk is evaporating with remarkable speed. For all homogeneous polynomials, let it be of degree p. A1, A p of degrees I1, IP, phi of A1, AP will have degree sum of I1 plus IP minus class K. Class K. In particular, for instance, if we take a polyvector field, so if phi is equal to the Hochschild-Kosten-Rosenberg map applied to some polyvector field P of degree P, what shall we have? Well, in this case, the degree of the result will be equal to the sum of degrees, right, minus the number of terms here, right, because every term is just one differentiation, and differentiation decreases the degree by 1. Yeah? And finally, but also we need to add the coefficients. So it will be equal to the degree of P as polynomial, the coefficients of P, minus small p. Claim. Damn it. Claim. Let us denote by C dot sub P in parentheses in the bottom of A comma A, a collection of all elements phi in C dot sub P of A comma A, such that degree of phi is equal to P. Then C dot P of A comma A is a subcomplex. So that H dot of A comma A will be isomorphic to the direct sum of H dot P A comma A. It's almost evident, in fact, right? It's almost evident. So the first statement follows directly from the fact that the multiplication preserves the degrees of homogeneous polynomials. And actually, when the differential in C dot is given by applying multiplication to certain elements. So it preserves the degrees, and then we apply phi again. The degree will drop in the same way as before. Moreover, Gerstenhaber bracket is homogeneous in the sense that it has to have a bracket of elements phi of degree p, degree in this new sense, of course, and psi of degree q will be equal, will belong to C dot P plus Q of A comma A. Right? Again, it's almost evident because this is given by substitution. And if we have dropped our degree first by Q, then we drop the general degree by P plus Q. Now, let us look at this formula. The degree of chi is equal to the degree of the coefficients of this polynomial, right? Of this polyvector field, minus the number of entries. For instance, it follows that HP of A comma A will vanish HP let me be Q if and whenever P is less than minus Q. Because every element here is representable by a Q vector field. And degree of every Q vector field is greater or equal to minus Q plus something. The lowest possible degree appears when the coefficients of this polyvector field are constant. Okay? And that actually is what we need, because if we take the canonical pi, the canonical bivector, then degree of pi will be equal to minus 1, right? So let us go on. I'm going to construct the star product now. I begin with the first term. So I'll construct the star product on SG. Damn it. So we begin with putting B1 equal to the Hochschild-Kosten-Rosenberg map applied to the bivector pi. It will mean in particular that B1 of AB is equal to, well, first of all, B1 is closed. That's first, because it's in the image of Hochschild-Kosten-Rosenberg map, so it should be closed. And also, B1 of AB is equal to minus B1 of BA. So let us now look for B2. B2 should verify the condition that delta of B2 is equal to the 1/2 of B1 comma B1. So what is this B1 comma B1? Let me recall it is equal to, when we apply it to A, B, C, it is equal to B1 of B1 A, B, comma C minus B1 of A, comma B, 1 BC. I claim that this is symmetric. This is symmetric. In the sense, when I anti-symmetrize it, it vanishes. The right-hand side vanishes. The right-hand side vanishes when it is symmetrized. Well, I'd rather say anti-symmetrized, right? I would recommend you to do this yourself. It's actually not very hard to prove. It follows directly from the fact that B1 is skew-symmetric. So you just check that when you take the anti-symmetrization of this term, you get 0. So it follows that the cohomology class of this expression is trivial in H3. You see why? Because you remember that every cocycle in what do you call this, in C diff of A comma A has the form. Let's know this cycle by Q. So Q will be equal to the symmetrization of Q plus delta of something. Right? So it means that if symmetrization is 0, then Q is just equal to delta of something. So now, if we symmetrize the right-hand side, or just I'd rather say anti-symmetrize, and it vanishes, which is possible to check using this symmetrization, right? We conclude that B2 always exists. So there always exists B2. It just follows from a symmetricity, nothing else. So you see this technical assumption about symmetricity plays a role here. Unfortunately, this is not yet enough for us to say something about the cohomology class of B2 and B1. You see that the next term, we verify the condition, 1/2 of this should be equal to delta of B3. I'd rather say this plus, I think, this. But it's not very important, actually, 1/2 of this. Right? So B1 is degree -1, right? B2, so the right-hand side is a degree -2, and delta preserves the degrees. So degree of B2 is -2. And finally, degree of the right-hand side here is -3. The degree is -3. Therefore, unfortunately, this degree is equal to the degree in the sense of Hochschild homology. And we cannot yet use that observation that whenever the degree in terms of Hochschild homology is less than minus the degree of, in the sense of graded algebra, this class should be 0, right? So, but on the other hand, but what we can do, we can not yet But what we can do, we can say that B2 can be chosen symmetric. That is to say, B2 of AB is equal to B2 of BA. In the sense, how can you prove this? B2 verifies this condition. If you symmetrize B2, suppose B2 is not symmetric, you just change B2 of AB to B2, 1/2 B2 of AB plus B2 of BA. Right? And then you check that this, since the algebra is commutative, that this expression will verify the same equation. Delta of this B tilde 2 will be equal to delta of B2. Right? It's not very hard. And now we can do the same trick here. B2 is symmetric, B1 is skew symmetric. Now we symmetrize the right-hand side, or anti-symmetrize, and see that it vanishes identically. So we can still find B3. And from that moment on, the existence of B4, B5, and so on is guaranteed by the structure of Hochschild cohomology. Because it all vanishes whenever the degree of the element as in sense of Hochschild cohomology is less than minus the degree in the sense of graded algebra. So that's more or less it. That's how you can construct the deformation quantization in the case of algebra, of polynomial algebra on a Lie group. And it is a good exercise to prove that this algebra is in fact isomorphic to the universal enveloping algebra of the manifold. Sorry, oh, not of the Lie group, of the Lie algebra. Okay. And that's actually is an alternative way to prove the Poincare-Birkhoff-Witt theorem. Pretty complicated, but
like
nice.
Vector space.
Yeah, of course. The Poincare-Birkhoff-Witt theorem is about this. Okay, I can stop here now.